further equation problems. So what we're going to do this week is have a look at some solutions to some different order equations and have a look at some kind of engineering examples as well. Right, here we go. So we're going to have a look at some further first order differential equations today. Right. If we have an equation form dy by dx is equal to a function of y, we can solve that by first rearranging. Give dx is equal to dy over the function of y. So we rearrange, so we've got dx on one side and the y terms on the other. And then we integrate both sides to find a solution by direct integration, using the variety of integration techniques that we have at our disposal. So we'll consider an example. Find the general solution of dy is equal to 3 plus 2y. So that is in the form of dy by dx is equal to some function y. Okay. So if we take that function we rearrange that so it's got x on its own, that's the first thing we're effectively doing. Yep, this comes up here and that goes down. So we end up x is equal to over 3 plus 2y. Integrate both sides. Just rearrange. Integrate both sides. So we go you might better see what we've got to do if you were to write that like this. What method do we need to use to integrate that right-hand function? Yeah, that's one of them, Lewis. We've got one fraction, so it's not separated fractions, is it? Substitution is the one. Yeah. So by substitution, for right-hand side, what do we need to do then? How does substitution work? You know how to pick it, but how does it work? This is what we've got to start getting off pat now. We've that and look at that exam question and say, I need to do that by substitution, and this is how I do it. There's no formula for it, it's a method. I'll remind you, let u equal 3 plus 2y. Yeah? Therefore, the integral of 1 over 3 plus 2y du dy, sorry, is equal to the integral of 1 over u dy. Now does it look like something in the table? Of standard integrals? ln, yeah? Yeah, substitute u back in, so it is equal to ln brackets 3 plus 2y. And when we integrate the left-hand side, we're just left with x. The final solution is that x is equal to ln brackets 3 plus 2y plus c. So, the solving of differential equations is going to involve you using the various methods of integration that we've learned earlier in the module. Yeah, by parts, by substitution, by partial fractions maybe. Okay? So that's general solution. Second problem, determine a particular solution of y squared minus 1 dy by dx is equal to 3y. Given that y is equal to 1 and x is equal to 2 and a 6. So we've got some boundary conditions now. We can find a particular solution. But first, to find the general solution. So how are we going to do that? We've got this function, y squared minus 1 in brackets dy by dx is equal to 3y. We know we want dx on its own. How are we going to rearrange that? Multiply by, divide by, yeah. So we can write dy by dx is equal to 3y over y squared minus 1. Next, you're saying the right thing, but the easiest way is invert both sides. Yeah, it's going to bring dx up the top where we want it. Yeah, so we can go dx over dy is equal to y squared minus 1 over 3y. Yeah. And then finally, what can we do? Yeah. Can you see how we can simplify that? Y squared, we can split that to y squared over 3y minus 1 over y. Now what will happen to it? Tell me something else we can do. Now we've done that. The left-hand part of the right-hand side. We can do something even more important than that. That goes, and that goes. Yeah, so we got dx is equal to y over 3 minus 1 over y. And we want to integrate both sides. Yeah? We can do that now, they're separate. Sorry? Where's that? At least have dy on the end. Really? Yeah, that's better. And that should have dy there as well too. That originated, Jake, from this one, yeah, separating that into two fractions. So you with that common denominator of 3y, it's just that in the left-hand side of that y cancels, and the square disappears, becomes a frame y. So these are two functions of y, one subtracted from the other. When we integrate those, we end up with x is equal to, if we integrate y over 3, what do we get? Yep. Do it like that if you like. What do you want to do? Where's the problem, Jack? Spotted. Boys, you are good. You're good at spotting. See where you are now. I don't mean to. That's why it's important to get you come up next to what you were looking at there. Sorry. Alright? Well spotted. Now where are we going? How do we integrate y over 3? Well, let's integrate y for a minute. What's the process? What's the index of y? So what do? Add 1 to the index. Yeah. And divide by the new index. So we got over 3 times 2, which is 6. Prefer to look at it as taking a third outside and then integrating y on its own. You'll still end, you'll be doing, that is the third of the integral of y on its own. Yeah, so you'll go a third times y squared over 2. Do you see where it comes from? Yeah? Alright? So that's that bit integrated. How do we integrate this? Again, we can write that as a separate integral with a third integral sign, can't we? Now how do we, what's the integral for 1 over y? So that's minus third ln 1 c. Boundary condition. Which were right, where were we before we were rudely interrupted? Y is equal to 1 when x is equal to 2 and a 6. So we put those in the function. Two to the 6th is equal to 1 squared over 6 minus a third ln 1 plus c. That bit is just a 6 minus a third of ln 1 plus c. You've got to rearrange that to find c. So that's c is equal to 2 to the 6th minus 1/6 minus a third and then 1. The original function y. Yeah. When we integrated, we ended up with y squared term there. Yeah, so I'm now putting the boundary conditions in as that when x is 2 to the 6th, which I'll put in the front, Jake, yeah? Y is equal to 1, that's why there's a 1 squared there, that's why there's a 1 inside the ln, alright? Yeah. What do we find c as being equal to? 2. So therefore, particular solution is equal to y squared over 6 minus a third ln y plus 2. Yeah. What I have to do now is have a look at an engineering related problem to this. So the variation of resistance R ohms of an aluminium conductor with temperature theta degrees C is given by the formula dr by d theta is equal to alpha times R, where alpha is the temperature coefficient of resistance of aluminium. Yep. So that's what alpha represents, a constant for the material. If R is equal to RO when theta is equal to 0 degrees C, solve the equation for R. So we're looking to find an equation that says d theta equals something in terms of R. Okay, so we want to go through the process that we've been going through to end up with an equation that says theta is equal to something in terms of R. So we need to rearrange that so we've got the theta on one side and the R terms on the other side. So if we invert, we get that. Yeah, everyone agree? Therefore, d theta is equal to 1 over alpha R dr. Yeah, you can. I don't know whether you do, but I find that more understandable if I put that multiplied by dr on the end. Yeah. If you can do, but what you want to realise as far as integrating that term is concerned is that is a 1 over fraction, and then you can see that. And I think that's more understandable that way. Tell me if you disagree. So now we need to integrate both sides. So we take the integral of d theta. What's the constant involved here that we could take outside an integral, which is what you guys seem to prefer? 1 over alpha times the integral of 1 over R dr. This is just a straight integration. That's something we can integrate directly from the table, bearing in mind that that's got a constant, that's multiplied by a constant of 1 over alpha. This just general integration from the table, these are, yeah. That was only that first one that required substitution, yeah. So d theta equals, what's the integral of 1 over R? So that must be 1 over alpha ln R plus C is the general solution. Theta, yes. Not on form today again, am I? You spot my deliberate mistake, Jack and Dom. Okay. You ain't got there yet. You've got to insert the boundary conditions for that now. So insert boundary conditions. Which were R is equal to RO when theta is equal to 0 degrees C. So we insert them in our function. 0 is equal to 1 over alpha ln RO plus C. We need to rearrange that so we've got C on its own. Yeah, because theta is 0 when R is equal to RO. Minus C is equal to 1 over alpha ln R0. How can we get that to a... So what is C? Must be minus all that lot, mustn't it? C is equal to minus 1 over alpha ln RO. We effectively just multiply both sides by minus 1. Hence, particular solution is temperature is equal to 1 over alpha ln R minus 1 over alpha ln RO. Can we simplify that at all? Okay. Is that what you mean? So, general solution has got an unknown arbitrary constant. You then use the boundary conditions, which aren't numbers in this case, just saying that R is equal to RO. You're saying R is equal to the material's resistance at 0 degrees C when the temperature is 0 degrees C. You're then coming up with a particular solution for temperature in terms of R and RO, and we got the temperature coefficient of the material in there. So now we do part B, which is alpha is equal to 38 times 10 to the minus 4 per degree C. want to know what the resistance is at 50 degrees Celsius for 3 different figures. So R's the question mark. Yeah. So we got to put those figures into that equation. Uh, 50 is equal to 1 over alpha 38 times 10 to the minus 4 times ln r at 50 minus ln we've got to rearrange that now. How do we go about doing that? Can you remember, just before we go into that, can you remember the laws of logarithms for one log subtracted from another? Because there is actually, the point I'm making is a further simplification of that solution. Yeah. Laws of logarithms. You just got that bird book. Have a look. Have you not? You don't remember the laws of logarithms. So we can write this as does that make it any easier? Do you think? Not Q, theta. Let's get rid of this. 50 is the temperature we want to know the resistance, what the resistance of the material is at 50 degrees C. So that's 50 is the temperature, and that's equal to 1 over alpha, 38 times 10 to the minus 4, ln R, which is what we want, over RO. got a value for RO as well here somewhere, haven't we? 24, yeah. Hang on. And RO is equal to 24. Yeah. That's the resistance when the temperature is 0 degrees C. So we can put that in here now. 24 in there. We'll subscript that with a 50 as well, so we know we're talking about the resistance at 50 degrees C. Yeah? So we're going to go 50 times 38 times 10 to the minus 4 on that side is equal to ln R50 to the 24. How do we get rid of the log function to get R0 out of that fraction? You do e to the power of both sides. If you look at your calculator, e to the power of x is the inverse or the shift function on the ln key. Yeah. So we take the e to the power of both sides. Yeah. And then we multiply by 24. So we're R at 50 is equal to 24 e to 50 times 38 times 10 to the minus 4. In terms of the original function, that's R at a temperature theta is equal to RO E to the power of theta times alpha, isn't it? Hang on, 50 is, no, 50 is R, isn't it? Not that bigger. Right underneath there. This is the temperature that we're looking for. 24 comes from RO. That's times E to the power of alpha times the current temperature is the form of that, and that's the version with our numbers in it. If you plug that in the calculator, what do you get? The three significant figures. So 29.0 here. Yeah. Alright. So look, once you, the problem is once you introduce that into an engineering problem, that looks a lot more tricky, but you're just following the same process as what you would if you're just working with a plain function. Alright. And over the next couple of weeks in the revision weeks, we'll practice engineering problems, and if you can see the type of thing that you're going to get. All right. In your handouts towards the end, there's a set of further problems on equations of the form dy by dx is equal to a function of y. So we'll go through the next bit, and then the end of the session, and between now and next week there's some more problems there you can have a go at, because like I always say, you can't get too much practice at these. Alright? What we're going to look at now is solutions to the equation of the form where dy by dx is equal to a function of y times a function of x, times a function of y, where fx is a function of x only and fy is a function of y only. We can solve these by rearranging to get all the y parts on one side and all the x parts on the other, and then integrating both sides. Okay, so again, true to form, we'll go through some examples together, see how we get on. Alright, so we're going to solve the equation 4xy dy by dx is equal to y squared minus 1. So the first thing we need to do is rearrange to separate the variables. X is on one side, y is on the other. So let's have a look at this function. 4xy dy by dx is equal to y squared minus 1. What's the first thing you would do in terms of getting all the y parts one side and all the x parts the other? Sorry? Why would you, if you divide by 4xy, you're going to put an x on the other side. Which side are you going to put things? Let's have all the y terms on the left, all the x terms on the right. Does that help? Divide by dy. Y terms on the left, please. You can't just do that. Divide by y. Yeah. I want the x terms on the right and the y terms on the left. Don't need to do anything with the 4. The 4 can stay where it is. Multiply by dx. Let's have that. I like that. Yeah, go on, divide by x. I want x is on that side, remember. So don't divide by y. 4y dy is equal to y squared minus 1 dx over x. Happy? Now what can we do? That's all together. That top line can be written as 1 times y squared minus 1. So we can divide by y squared minus 1. What's left on this side? Yeah. No need to move the 4. That's just a number. Yeah. Yeah, but what I'm not saying that isn't quicker if you see it that way. But I wanted to show the step-by-step process, because some people don't get it quite as quickly as you. Right? Yeah. Okay. You want to explain exactly what you mean? Yeah. You end up with the same. You moved the y's to the right, which makes no difference. You still end up with the same thing, don't you? Still end up with what we end up with. Yeah? But you're doing it very quickly, understanding the whole thing in one go, and I'm just trying to show it step by step. Okay? Yeah. You would end up with 4, and you can end up with 4x there, but you'll end up with the same answer. But I don't see the point in moving the 4, or leaving the 4. Yeah. No, because the 4 will come down there, well, that'll be 1 over 4x. Yeah. Now what do we want to do? We want to integrate both sides, don't we? Integral of 4y over y squared minus 1 dy is equal to the integral of 1 over x dx. That side's easy. What about this side? How are we going to do that side? I'm asking you how you do it. What's the method? What do you mean? Listen to it spoken out doesn't work. Okay. you squared the top y, but only multiplied the bottom by 2. No, you can't. No, because no, you can't do that. No. How do we do it? Can we do substitution? So doing this bit, let u equal y squared minus 1. So then we're looking at change colour. We're only doing this side at the moment. That bit is, what's the answer to that bit? So that bit's solved. Yeah. So we're looking at the integral of 4y over u dy. This is what he... I don't get this. We've still got a y in there, haven't we? Just tell me what you've done there. What here? That definitely goes as ln x plus c. Yep. Because you're integrating 1 over x. What's your final answer, Seppi? You just tell me. A minute, you're rewriting this bit. You're saying you're going to write that as 4 over. No, well, yeah. No, how do you do that? That would be writing this as 4y over y squared minus 4y over 1. Now you can do that. Has that helped? No. That's the point I'm making. You can't cancel when you got that 1 there.
When we scroll up to the right,
Yeah?
go on offset, you've got four wires, one straight line,
Yep. You got 1 of a DX on the right hand side then. No, because that is, you could write that as dx over x. If you invert it, that's x over dx. It's not the same thing. How's that done by substitution? Because the man says that's done by substitution. Doesn't go into the detail. So how do we do that by substitution? He says it ends up as 2 ln y squared minus 1. That's what he says that ends up as, integrating that by substitution. So we let u equal y squared minus 1. Then we rewrite that integral as 4y over u by dy. Am I right in that? That's what you would do. Yeah? Equals the integral of 1 over u times 4y. Yeah? So that's where the 2 come from, isn't it? So if we integrate 4y, what do? We do y. No, take 1 off, don't we? Add 1. We're integrating. Y squared over 2. Yeah. So that becomes 2, doesn't it? Yeah. Yeah, but you can't pick it up, can you? We've got to differentiate this. dy by du is equal to and then we got to arrange that for take 1 off the in, multiply by ax to the n. Differentiating a and x becomes 2y. It's better, not half y. Becomes 2y. Therefore, dy is equal to that help? Check the process. We rearrange it for have we done that right? At the moment, we're differentiating what we've called u. So the constant disappears, and that becomes 2y. So we're now going to integrate four y over u, because that's what we're replacing that with. We're going to replace dy with 2y du. How does that cancel that bloody 4y? I've had enough today. That is the answer.